Somewhere in the constellation Leo, there is a star so ancient that its very existence appears to contradict what we understand about how stars form. Its light has traveled from nearly the beginning of time itself, and the chemistry locked inside it tells a story that our models of stellar birth struggle to explain. This star carries the designation SDSS J102915+172927, though it is also known as Caffau's star, named after the astronomer who led the team that characterized it. It resides in the galactic halo, that vast, sparse sphere of ancient stars that surrounds the disk of the Milky Way. Its estimated age is approximately 13 billion years, placing its formation in the earliest epoch of the universe, when the cosmos was perhaps only a few 100 million years old. Among the billions of stars we have catalogued, this one stands apart not for its brightness or its size, but for what it lacks. To grasp that timescale, consider this. The universe itself, according to the current concordance cosmology, is approximately 13.8 billion years old. Caffau's star formed so close to that boundary that it belongs to one of the first generations of stars ever to ignite. It is a population 2 star, meaning it formed from gas that had already been lightly enriched by an even earlier generation, but only barely. The enrichment was so slight that it barely registers on our instruments. What was observed about this star upended a central expectation in stellar physics. At the time of its discovery, Caffau's star held the record for the lowest metallicity of any known star. In astronomical terms, metallicity refers to the abundance of elements heavier than hydrogen and helium. This star is deficient in carbon, nitrogen, and oxygen. More remarkably, it is completely devoid of lithium. That combination of absences is what makes this object so confrontational to theory. Now here is where the conflict between observation and theory becomes truly striking. The prevailing models of low-mass star formation depend on something called fine structure cooling. When a cloud of interstellar gas begins to collapse under gravity, it heats up. For that cloud to continue contracting and eventually form a small, long-lived star, it must radiate away that thermal energy. Carbon and oxygen are the primary agents of this cooling at low temperatures. Their atomic transitions allow the gas to shed heat efficiently, fragmenting into smaller clumps that become low-mass stars. Without sufficient carbon and oxygen, the theory predicts that gas clouds can only form massive stars, objects that burn fast and die young. The critical metallicity threshold, established through both theoretical modeling and observational surveys, is estimated to fall somewhere between 1.5 times 10 to the -8 and 1.5 times 10 to the -6 of solar metallicity. Below that range, low-mass star formation should not proceed. The physics is clear, the prediction is firm, and the star ignores it entirely. And yet Caffau's star exists. It is small, it is low mass, and its carbon and oxygen abundances fall below the levels that theory requires for its own formation. This is not a marginal discrepancy. The star sits in a region of chemical parameter space where our models say it should not be. It persists as a quiet contradiction, burning steadily for 13 billion years, while the equations say it never should have ignited. The detection came through the Sloan Digital Sky Survey, which provided the initial identification, followed by detailed spectroscopic analysis that revealed the extraordinary chemical poverty of this object. Spectroscopy remains our most powerful tool for dissecting the composition of distant stars. Each element absorbs light at characteristic wavelengths, leaving fingerprints in the stellar spectrum. In the case of Caffau's star, those fingerprints for carbon, nitrogen, oxygen, and lithium were either faint to the point of near absence or entirely missing. The observational limits here matter considerably. Measuring extremely low abundances pushes instruments toward their detection thresholds. At such low metallicities, spectral lines become vanishingly weak, and the signal can be difficult to separate from noise. The lithium non-detection is particularly significant because standard Big Bang nucleosynthesis predicts a baseline lithium abundance in primordial gas. Its complete absence adds another layer of mystery, though lithium depletion mechanisms in old stars remain an active area of study. We must be careful to distinguish what is truly absent from what is merely below our ability to detect. So what explanations have been proposed, and how do they rank against the evidence? The leading class of hypotheses centers on alternative cooling mechanisms. If carbon and oxygen were not available in sufficient quantities, perhaps another process allowed the gas to cool and fragment. Dust grains in the early interstellar medium, even in trace amounts, could provide radiative cooling through thermal emission. Molecular hydrogen, under certain density conditions, can also contribute to cooling, though less efficiently than metal line radiation. A second possibility involves the geometry of the star-forming environment itself. If Caffau's star formed in the dense shell of a supernova remnant from a first-generation star, the compression and turbulence in that shell might have enabled fragmentation despite the low metallicity. The enrichment would have been uneven, with some pockets of gas receiving fewer metals than others, yet still experiencing the physical conditions necessary to collapse into small objects. This scenario is plausible but difficult to test directly, since the environment that birthed this star dispersed billions of years ago. A third hypothesis questions whether our metallicity threshold models are simply too restrictive. The critical metallicity is derived from simulations that necessarily make simplifying assumptions about gas geometry, radiation fields, and magnetic support. If the real universe permitted a broader range of initial conditions, the threshold might be lower than calculated, or it might not be a sharp boundary at all, but rather a probabilistic one, where formation becomes unlikely but not impossible. The best current explanation, ranked by the weight of theoretical support, is that some combination of dust cooling and localized compression from nearby supernovae permitted this star to form in conditions that pure metal line cooling models would forbid. This does not resolve the question fully. It shifts the problem from impossible to improbable, and improbable events, given the vast number of star-forming regions in the early universe, can still occur. The universe had hundreds of millions of years and countless collapsing clouds in which to find those rare pathways. What could settle this? Future observations with next-generation spectroscopic instruments could detect even fainter elemental signatures that current instruments miss. If trace amounts of carbon or oxygen exist below present detection limits, the tension with theory would relax considerably. Alternatively, finding more stars in this same ultra-low metallicity range would test whether Caffau's star is a genuine outlier or a representative of a broader population that formed through mechanisms we have not yet modeled adequately. Surveys targeting the galactic halo with improved sensitivity could reveal whether dust cooling at early epochs was more common than currently assumed, providing indirect support for the leading hypothesis. Each new detection or confirmed absence narrows the range of viable formation pathways. What Caffau's star ultimately teaches us is something about the relationship between models and the universe they attempt to describe. Our theories of star formation are built on physics we understand well: radiative transfer, gravitational collapse, thermodynamics. But the early universe was not obligated to explore only the parameter space our simulations have covered. A single small star in the halo of the Milky Way, burning quietly for 13 billion years, carries in its impoverished spectrum a message about the limits of prediction. It does not break physics. It reminds us that the cosmos found pathways to creation that we have not yet fully mapped. Somewhere in those first few 100 million years, in a cloud of gas almost entirely composed of hydrogen and helium, something cooled, something fragmented, and something ignited. The star that should not exist has been shining ever since, older than nearly everything else that remains, patient and indifferent to the confusion it causes. And in that patience lies a challenge, not to our physics, but to our certainty about how completely we have understood the first light of creation.